Excuse me. And looking at what the theorem states here, it says if f is continuous on the closed interval AB and differentiable on the open interval AB, then there is at least one point C inside the interval where f of b minus f of a over b minus a is equal to f prime of c. So remember this, this is the slope of our secant line, and f prime would be the slope of our tangent line. Okay, so just like the picture that we saw in the previous slide, what it's suggesting is, okay, when I've got some smooth continuous curve on some interval from A to B, right, then there has to be some point in between that has a slope that's equal to the slope of the secant line. So actually, let me draw a different curve that I can exaggerate it a little bit here. So there's the secant line there connecting the points. So that would be, the slope of that would be what we have here. And then there's got to be at least one point on the curve somewhere where the slope of the tangent line, if we imagine maybe about right there, slope of the tangent line is equal to the slope of the secant line. So there's some point C in between here. Okay. So with the picture, I think it makes sense. And we'll see why this is an important theorem because of all the consequences of it. In other words, lots of important conclusions can be made once we've established this. But let's think about an example where we can put this into context a little bit. Okay, so this one kind of sets it up a little bit with defining something called the lapse rate. It says the lapse rate is the rate at which the temperature T decreases in the atmosphere with respect to increasing altitude Z. It is typically reported in units of degrees Celsius per kilometer and is defined as gamma equals negative dT over dz. So it's the negative derivative of temperature with respect to z, which is the altitude. When the lapse rate rises above 7 degrees Celsius per kilometer in a certain layer of the atmosphere, it indicates favorable conditions for thunderstorm and tornado formation, provided other atmospheric conditions are present. So yeah, actually, before I look at the picture there, let's think about this lapse rate function gamma. Let me see here. So what I want to first do is let's suppose that the temperature at an altitude of 2.9 kilometers is 7.6 degrees Celsius. And then we look at a different altitude. So the temperature at Z equals 5.6 kilometers and an altitude of 5.6 kilometers is T equals negative 14.3 degrees Celsius. Okay. So now let's also assume that the temperature function is continuous and differentiable at all these altitudes so that we can use the mean value theorem. So we'll assume the temperature as a function of altitude is continuous and differentiable. So what can we conclude? So if you're a meteorologist, what can a meteorologist conclude from this data? Meteorologist. Hold on, I think my cat's gonna barf. Okay, sorry about that. Okay, so anyways, coming back to the problem here. Well, let's remember if we're defining the lapse rate to be the negative derivative with respect to Z of the negative derivative of temperature with respect to Z, and we know that if this goes above 7 degrees, then we're looking at the possibility of there being favorable conditions for a thunderstorm and in our tornado formation, right? So in this case here, could we argue somehow that the lapse rate is going to go above 7 degrees Celsius and create favorable conditions for a thunderstorm? Well, let's look at it a little bit. So let's see on the, say we're on the interval, right, where Z is between 2.9 to 5.6. We see that according to the mean value theorem, there must exist a point C in the interval from 2.9 to 5.6, where dz, or sorry, the derivative of temperature, well, here I'll write it this way, where t prime of C is equal to T of 5.6 minus T of 2.9 over 5.6 minus 2.9. We said the temperature at 5.6 was negative 14.3 minus the temperature at 2.9 was 7.6. And let's just see quickly what that evaluates to. So here I get something around negative 8.11. So what does that tell us about the lapse rate? So basically it tells us that because here the lapse rate is the negative derivative, it's the negative of that. So there must be an altitude where the lapse rate gamma is equal to negative dt over dz. And here we got negative 8.11 for some t prime. So that would be negative 8.11. Which is definitely bigger than 7, right? So it implies that there is favorable conditions for a thunderstorm and tornado formation. Okay. Which actually here, if we think about it, right? Because the mean value theorem suggests that there would be a point where the derivative is equal to this. Then of course it's also got to, hit all the values coming up to that 8.11 because it's continuous. So that would also imply that with the intermediate value theorem, it's going to also include some other values that are greater than 7. So looking at here, let's look at a graph that could potentially represent this scenario, right? Where we know the temperature at these 2 points, right? One was at an altitude 2.9 kilometers, another was an altitude of 5.6 kilometers. And we observed that here the temperature, right, is going down from 7.6 degrees to negative 14.3 degrees. Where because we can find the slope of that line there, we don't exactly know what the temperature curve is, but we can argue that by the mean value theorem, there must be some point in between here where the rate of change is what we said, negative 8.1. And so therefore it must have some points where the lapse rate goes above 7. Okay, so yeah, this is just maybe one possible example of what a temperature curve might look like, but any other possible temperature curve that I draw as long as it's continuous and differentiable, must have a point where the tangent has a slope of negative 8.1.